This lecture will cover some basics on phase diagrams and heating curves. You also have some worksheets that will provide you with additional information to supplement what we'll go over in this lecture. Make sure that you have your objective sheet, a calculator, and you will not need it in this lecture, but when you are doing practice problems, you'll want to make sure that you have a periodic table because there will be times that you need to convert from grams to moles. So phase diagrams and heating curves, what do they show us? What do they provide us? Well, they allow us to learn about substances and their transition between multiple phases. So we can look at when a substance is in its solid state, when it's in a liquid, when it's in a gas, at what temperature does this occur, at what pressure does this occur. So we'll be looking at things like that. So this is an example of a phase diagram. You also have one in your unit packet that you can reference as well. So as you can see, we have pressure going up our y and temperature going along our x-axis here. So we'll talk about a few things. These lines in between, you can see that we have solids here, we have liquids here, and we have gases right here. Now, what these lines represent is when those two phases are in equilibrium. So when we are essentially transitioning from one to another. So if we are looking at line D here, that I'll highlight for you in green, that is our transition from either solid to liquid or from a liquid to a solid. So you can look on your phase diagram worksheet. It will give you the names of all of those, most of those that you are aware of already. The ones that you may not be aware of and you may not even think happens is going from a solid to a gas or from a gas to a solid, because traditionally we think of when we go from one phase to the next, it's going solid, liquid to gas, gas, liquid to solid. But that does happen, and what you can see is that it happens most of the time, we'll say, when your pressure is very low, so we're in a low pressure, and when you're in a low temperature. So that's when you're going to see that transition happen, most of the time going straight from a solid to a gas. So you're going to want to also note some things, some points on your graph. Right here, where all three of them meet together, is called a triple point. And the triple point is when all three states are in equilibrium. So it's very similar to what the line represents as we're transitioning from one to another. But at this point right here, all of them are in equilibrium, and it, depending on, do we increase our pressure, do we decrease our pressure, do we increase our temperature, decrease it, do we increase both, do we decrease both, that is going to depend on, is that substance moving to a solid phase, a liquid phase, a gas phase. But at that triple point, all three of them are in equilibrium. We are also going to see a point on the curve called a critical point, and you'll generally find this up in the top right-hand corner. So there's really not a technical critical point on this, but you'll see it somewhere around here. Let's up here by the C. You'll see that critical point. And what this means is that we're at a temperature and a pressure in which we can no longer distinguish between solids and gases. So it's going to be at a very high pressure and at a very high temperature as well that we will see this. So now you kind of have an idea of what you're looking at with your phase diagram. So we'll take a look. Well, this is a good, you can pause this, copy this down if you want to. This just shows you the different names of the transitions between different phases. This is also on your phase diagram worksheet. What I like about this one is it gives you your delta H's as positives or negatives here, which indicates to you if they're going to be exothermic or endothermic reactions. So that's why I like this. You might want to copy this down. Okay, so analyzing phase diagrams. What can I ask you? What type of questions will you see on phase diagrams? So I could ask you things like, at what pressure and temperature will you find all three states at equilibrium? Well, knowing that all three states at equilibrium is your triple point, you would find that triple point and then you would tell me that the temperature would be 0.01 degrees C and your pressure would be 0.6 kilopascals. What else could you see? Maybe I give you at a pressure of 50 and a temperature of 10. So pressure of 50 is going to be about right there. A temperature of 10 degrees is going to be down here. In what phase will I be in? Well, let's just make those lines come together. And at a temperature of 10 and a pressure of 50, we're looking at a liquid. Maybe I ask you at what temperature is the critical point. Well, the critical point here is already labeled for you. It's not always going to be labeled. It depends on what phase diagram you're looking at. But here's our critical point. So that would be at 374 degrees C. Now, you're not always going to have these be exact. This one does this specifically for this purpose here, that we can get the exact numbers. But you're going to see it like a regular graph where you're looking at your temperature going up by 10s and your pressure going up by 50s or whatever the scale is. And then you may have to estimate. Now, if you have to estimate, that's okay, as long as you are estimating within the ballpark range. So reading these graphs is not too difficult once you understand what you're looking at. You're going to see your pressure here, your temperature here, and then just remember solid, liquid, and gas phases. Okay, so the next thing we have is a heating curve. Now, a heating curve is also going to show us the same thing. We're looking at transitions between different phases, but what it's going to give us is the temperature change over time. Now, each of these steps, so this kind of looks like a staircase, each of these steps is going to represent different things. So we're going to start at the bottom left here. So you may want to pause this and draw a rough sketch of this. Notice there is no scale on here. So right now we're just looking at what is the heating curve, what do the different parts represent. We will do some with some scales once we start doing a little bit of calculations. So we're going to start at the bottom left here. And this is going to be when your solid is getting hotter. So a lot of the times it helps if we think of this as a heating curve for water because we're familiar with the phases of water. So this is when you have ice. Now, we all know that at a certain point of a temperature, we're going to have ice. But that ice can get warmer and remain ice. That's what we're looking at here. So we're in a solid phase right there. But my solid is continuing to get warm, but it still is remaining a solid. So your ice cube is still an ice cube when you're down here. So our next one is when your solid is changing to a liquid. So now we know, okay, I've had my ice cube out on the counter in my cup, and now it's starting to melt. So what's happening here is it's going to be in both a solid and a liquid state. But what's happening is what we call a phase change. So the phase is changing, but notice what is not. The temperature is not. So here we're looking at a temperature change. And here we're looking at a phase change. So in your temperature changes, you're staying in the same phase. In a phase change, you're staying at the same temperature. Okay, so what happens to water, or to, yes, water after it melts, the ice melts all the way to liquid? It's just liquid water. So that's what we're looking at here. Now we all know that we can have a cup of water when it's cold outside, it's still water. We can have a cup of water when it's warm outside, it's still water. So our water can be in liquid phase in quite a very large range here. It's going to remain in that liquid phase. It's not going to get cold enough to become a solid again. It's not going to become hot enough to become a gas. So this is when my liquid is getting hotter. However, we know that eventually we're going to have a phase change where that liquid is going to start changing to a gas. When you're boiling water, what's going to happen? You start to see steam coming up. Well, that steam is it changing into your gas phase. So once again, here we're looking at a temperature change, and then when we flatline, we're looking at a phase change. And then after we are completely in the gas phase, or completely changed over to a gas, then we're in a gas phase where that gas can continue to get hotter and hotter, and it will remain as a gas. So remember that these flat lines here, no temperature, but a phase change, and then your other lines, your ones that are going up at angles, are when the phase is not changing but your temperature is. So I think it really helps if you think about it in terms of water, because we are familiar with water and how it works and how it changes from one substance to another. Okay, some equations that you're going to use. This first one here should look pretty familiar. Q equals mc delta T. So with heating curves, a lot of the times we're going to be looking for the total amount of energy that is used. Or maybe you're given the energy and you want to find how much the temperature has to change for us to use that much energy. But two new equations that you're going to have are your Q equals your mass times your heat of fusion. Now your heat of fusion is when you are changing from a solid to a liquid, or a liquid to a solid. So that's going to be that melting or that freezing phase where we flatlined out. Then heat of vaporization, well, think of when you hear the word vapor, you should be thinking gas, so that's going to involve your gas. That's going from a liquid to a gas, or a gas to a liquid. Now let's take a look. You can just add these equations to the drawing that you already did of the last heating curve. What I think helps to remember when to use these equations is when your temperature is changing, you're going to be using our little friend Q equals mc delta T, because you have a temperature change in the equation. If you do not have a temperature change, when you're just in a phase change, you're going to use either Q equals m times your heat of fusion, or Q equals m times your heat of vaporization, because your temperature is not changing, so it's not applicable to your equation. So let's look. Q1 is pointing to this first line. What equation do you think we're using here? Well, my temperature is changing, so I'm going to use Q equals mc delta T. The energy for step 2 here. My temperature is not changing, so I know that I'm using either my heat of fusion or my heat of vaporization. And knowing how to read this graph, we know we're going from a solid to a liquid, which means we're going to use our heat of fusion. Number 3, we have a temperature change, so we're using MC delta T. 4, we have no temperature change, so it's heat of fusion, heat of vaporization. We've already used the heat of fusion, so we're going to be using the heat of vaporization. And then in the 5th step here, we have a temperature change, so we're using MC delta T. So now let's take a look at a practice problem where you're going to have to kind of combine some of these equations here and learning how to use them. Calculating with heating curves. So anytime that you're going to be calculating, you're either going to be given things like the melting point and the boiling point, or you will be given a graph in which you will have to derive information from in order to use it. So this says for us to calculate the total energy when 30 grams of this substance is heated from 20 degrees to 90 degrees C. Now, one thing I see a lot of, and I want to make sure that we are aware of this, is a lot of the times we look at, we're going 20 to 70, so my delta T is 70. No, it is not. Yes, I'm changing from 20 to 90. However, you have to look at the different phases that you go through, and you're going to use your temperature change within each phase. So we're going to do this in multiple steps. So don't assume, okay, those are my temperature changes, I just subtract them to find the difference. Not necessarily. You're going to have to look at each step. So the substance is heated from 20 to 90. So we're starting here, and we are ending about here. Now, the reason it's not going to be 70 as your delta T every time is because we have two separate temperature changes. You have a temperature change here, and you have a temperature change here. So we're going to calculate those separately. So the first calculation we're going to do is going from 20 until we reach our flat line. That's going to be our first calculation. So with a temperature change, what equation are we going to use? Q equals MC delta T. So your C's are given to you. This is the first one right here, is your constant for your specific heat for your solid phase. And here's your specific heat for your liquid phase. Below that, you'll have the heat of fusion, and below that, you'll have the heat of vaporization. Okay, so let's take a look. We're solving for the energy, so we are solving for Q. So Q equals, M is my mass, that's 30 grams. C is my specific heat. Well, this first one we're looking at is in the solid phase, so we're going to use this one here, times 2.19 joules per gram degrees C. You're probably thinking, do I have to write all these units out? And you should know the answer to that. Yes. It's going to help to make sure you know which equation you're using, and there's going to be times where maybe you're given a heat of fusion that's joules per mole, and you are calculating everything in grams. It's going to give you an incorrect answer. So it helps you to make sure that your units cancel. And then my delta T. Well, we said it's not going to be 70, but look where I'm going from. I'm starting at 20, and I have to go until my melting point, which is at 40. So my delta T becomes 40 degrees, and that's going to be 40 degrees C. So let's type this in the calculator. 30 times 2.19 times 40 . Oh, you know what? I made a mistake. I hope you thought something was wrong there. This should be 20. I'm going to 40, but my change is 20. 30 times 2.19 times 20 gives me 1314 in my units. Let's take a look at those. Degrees C cancels, grams cancel, I'm left with joules. So for step 1 here, right here, we're looking at 1314 joules. So just to get me to melt whatever this substance is, I need to use 1,314 joules. Okay, so the next step, we'll highlight them as we go here. We've done this, so now we need to do this melting phase. So I'm going to erase our calculations here because we don't need them anymore. Now which equation are we going to use? Do we have a temperature change? No, we're looking here. No temperature change. So we do not want to use these because they have a unit of temperature in it. If we have that unit of temperature, it's not going to be able to cancel if we don't multiply it by a temperature. So we're either going to want to use the heat of fusion or the heat of vaporization. So knowing that the heat of fusion is what you're going to use when you're going from a solid to a liquid, we're going to use this heat of fusion. So Q equals my mass times my heat of fusion. So my mass is 30 grams. My heat of fusion is 450 joules per gram. Grams is on the top, grams is on the bottom of this unit, so I'm left with joules. 30 times 450 gives me 13,500 joules. So that's going to be here. All right, so let's highlight the next phase that we've already covered. So we've done this, and we've done this. Okay, so now we have our last phase here, and this is when we are heating our liquid. So we're looking right here. So, temperature change or no temperature change? You should be saying temperature change here. So if I have a temperature change, I don't want to use either of these, because they don't have a unit of temperature. We want to have a unit of temperature if we have a temperature change. So we're going to use one of these, which means we're using Q equals MC delta T. We're solving for Q. My mass is still 30 grams. Now which C do I use? Well, when I'm up here, I'm in the liquid phase. So I'm going to use this one, my specific heat of the liquid, 3.06 joules per gram Celsius, times my temperature change. Well, I'm starting out at 40 and I'm going to 90. So my temperature change is now 50 degrees C. So units, Celsius cancels, grams cancel. We're going to be left with joules, which is what we want here. So 30 times 3.06 times 50 is going to give me 4,590 joules. That's a 9. So now we have covered this phase. So we have been looking at the temperature change from this entire red part of this line. We did it in 3 different steps because if you look at it, you have step 1 here, step 2 here, and step 3 here. So we have to account for each of those steps. Now we're looking for the total energy going from 20 to 90. So what are we going to do with these 3 numbers? The 13,500, the 1314, and the 4590. We're just going to add them together. And we're going to get a total energy of 19,404 joules. Alright, so go ahead, take some practice looking at your phase diagrams and heating curves, and let me know if you are in need of any additional help.